All right, you guys, we're going to continue our discussion of composite functions. Now we're going to talk about how do you find the domain of a composite function, okay? So remember, domain is concerned with the inputs or the x values that you can plug into a function and you can get an answer for, all right? So because we're talking about composite functions, we have functions inside of functions. So the easiest way that I like to think about them is that your functions will act like filters, okay? And they will filter out which x's will be included in your domain. So whatever x values make it through both functions, those are the ones that you will include, okay? So I don't know if you guys have ever made spaghetti before, okay? But when you make spaghetti, all right, you typically use a strainer, right? So if you have all the noodles and the water, and I am not an artist, all right, and you put them into the first strainer, right? A strainer has holes, right? So the noodles will get stuck in the first strainer, all right, and the water comes out, okay? Then if you come through and get a second filter, all the water will come through here. Whatever's good will be contained in there, okay? So if you want to think about finding the domain like a strainer and pouring spaghetti noodles in it, you can do that. So the first thing we're going to do, we're going to start out with all x's possible. Let's change this color. All right, we would start with all x's possible, and we would place them into the first filter. That first filter is going to be your inner function, okay? So if you were dealing with f composed of g, okay, g of x would be the first filter. So you would figure out what x values can you plug into your inner function, and those would be the ones that would pass through the second filter, the first filter, sorry. All right, so the second filter would be the values that pass through your new composite function, okay? So you assess all the ones that made it through the first filter, then pour them into the second one. Whatever values come out at the bottom, those are the ones that are contained in your domain, okay? So we're going to do a problem so that you can see how this works, okay? All right, so our example says, suppose that f of x equals 1 over x plus 2 and g of x equals 4 over x minus 1. They want us to find f composed of g and for a, and b wants us to find f composed of f. Then find the domain of each composite function. All right, so let's do a first. So a wants us to find f composed of g, which I'm going to write like this. All right, so this tells me that g of x is my inside function. So that tells me everywhere that there's an x in the f function, I'm going to place the entire g function in its place, okay? So let's go through this slow. All right, so I'm going to write f of x. So f of x is 1 over x, but in its place, I'm going to put parentheses, all right, plus 2. All right. Now, where that parentheses is where x was, but it's where I'm going to put the g function. And the g function is 4 over x minus 1. Okay. So as you can see, the g function went exactly where x was in f of x. Okay. Now my job is to simplify this. Okay. All right. So 1 in the numerator stays the same. Okay, but in the denominator, now I have this rational and I have a whole number. The only way that you can add like a fraction and a whole number together is if you have a common denominator. So I need to multiply 2 by x minus 1 over x minus 1. Okay, when I do that, I'm left with 4 over x minus 1. This 2, I'm going to distribute to the numerator. So that's going to give me 2x minus 2 over x minus 1. Okay. Now that my bottom terms in the denominator have the same denominator, we're going to add their numerators. So I have 1 over 4 plus 2x minus 2 over x minus 1. I can combine like terms. So it's going to give me 1 over 4 minus 2 is 2 plus 2x over x minus 1. All right, so instead of dividing by a fraction, I can multiply by the reciprocal or keep change flip. So this is going to be 1 times x minus 1 over 2 plus 2x. And 1 times anything is just itself. So it gives me x minus 1 over 2 plus 2x. Okay, that is my composite function. All right. So not only did they want me to find the function, they also wanted me to find the domain. Okay. So we're going to do this over here. So we need to find the domain. All right. So we're going to think about them like the filters. Okay. So the first function that acts as our filter is going to be g of x, because g of x is our inside function. So if I look at g of x as the first filter, okay, and for us, the second filter is our composite function, which was f composed of g. All right, so let's see if we can pull out some important information about these functions. So if we look at g of x, okay, g of x is this function here that they originally gave us. All right, it looks like a fraction. We know that functions that look like fractions are rationals. Okay, and we know that when it comes to finding the domain of a rational, you can include any value for x that you want as long as the denominator does not equal 0. Okay, so if I go to find the domain of g of x, okay, I would set the denominator equal to 0. So I have x minus 1 equals 0, plus 1, x equals 1. So that means I can plug in any value I want into that function as long as x does not equal 1. So if we start with all of the x's, okay, then x equals 1 gets stuck into the first filter. So we already know it can't be included in the domain. All right. Then we check to see, all right, so after that, which values cleared the second filter? So the second filter is the composite function that we found. Okay. So we have to look and see, well, what type of function is it? Well, it's also a rational because it looks like a fraction. All right, which means that also its denominator cannot equal 0. Okay, so that means we need to set its denominator equal to 0 to find out which values we need to exclude. So I have 2 plus 2x cannot equal 0. We're going to find that. Minus 2, 2x equals negative 2 divided by 2. All right. And x cannot equal negative 1. All right. So all the x values, negative 1 gets stuck in the second filter. All right. So out of all those values, everything else clears. We're good with everything else. Okay. So that means that our domain, okay, are all x such that x does not equal, okay, 1, negative 1, and 1. All right.